So, our final speaker is Didier Queloz. He was born in Geneva, Switzerland in 1966. He did his undergraduate and PhD studies at the University of Geneva, and the PhD studies with Michel Mayor as supervisor. Didier Queloz is presently professor at the University of Geneva and the University of Cambridge in the UK. Please join me in welcoming Didier Queloz to the stage to tell us about the development that led to this year's Nobel Prize.
Thank you. So I'd like to thank the Nobel Foundation and the Royal Swedish Academy of Science for this great honor and the privilege to receive this award. And I really welcome in the audience my family, my colleagues, and absolutely delighted to share this exceptional moment with all of you today. I'd like to express my deepest gratitude to all the engineers and technicians and collaborators of the Observatoire de Haute-Provence and Geneva Observatory that could not come here today for their contributions to the constructions and the operations of the spectrograph Elodie I will be talking about. I mean, clearly without their work and the commitments, I would not be in front of you today talking about that story. So the story I'm trying to convey to you is the story of the detections of the first planet orbiting another star like the Sun, and the impact of the discovery of the fantastic growth of the field that followed up, and saying that we kind of created a new field of astrophysics. So on the screen, you do see the effect of a planet orbiting a star, and I think you got it right now that what you really see here is the motion of the star. And this is the effect that we've used with Michel to detect the planet orbiting the star 51 Peg. And if you pay attention to the motions, you may look, there is a kind of a wave that changed color. That's to picture what we call the Doppler effect, or so-called the redshift, blue shift, depending on the change of the speed of the star during the orbit. So the star has an orbit because the whole system is orbiting around the center of gravity, and when the planet that we don't see, it's invisible, actually makes a long orbit, the star makes a small one. This effect is very tiny but can be detected, and it took a long time to detect this. The principle was known since a long time, but the detection is really the challenge of it. And you have the telescope, which is us on the other side. So you may pick that is some part of the orbit when it's becoming blue and red. So how do you get to measure a speed of an object which is light years away from us? Well, you use the light coming from that object, and you make something that we call a spectra. So this is what looks a spectra, is you take the light, you spread the light in wavelength or in color, kind of a rainbow. You do that in a great detail, you measure the flux, and you realize that there is some part of the light that you don't see very much because there is absorptions. This is what we call the forest of absorption lines. This is the sun. Almost, it's a bit cooler than the sun in this case. And then what you see here is all the atoms that are in the atmosphere of the star that makes a kind of an imprint about how much they are, what is the temperature, what is the pressure into the stars. So there's a lot to do with this, but we make a very simple use of this. In our case, we just use that to compute the speed of a star. How does it work? When you change the speed of the star, the location of this line are moving. Actually, it's a stretch. So the heart of getting the speed of a star is getting a spectra and to measure that stretch. And that's it. That's really the way that you need to go if you want to pick up an orbiting planet on a star. Well, the problem is the effect is very tiny. So what happens here is, because this Doppler effect that picture the change of speed of the star is kind of a global effect. You can bring a very compact expressions of this by doing a trick, a mathematical trick that was thought in the 60s, which is using a match template when you know exactly where are the lines, and doing a mathematical process which is called cross correlations, and you build a cross correlation functions. So I show you the cross correlation functions of the star 51 Peg, and that's the kind of the raw data that we got, and that is the heart of the discovery of the planet. So these, in a way, is the kind of the average of all these lines you have in the spectra, all brought together by this mathematical trick, and you use this to compute the locations in speed. That's why you have the radial velocity. This is the terminology. You see kilometer per second on the horizontal axis, and you try to see a small motion of this. That's all about it. So that was my data stuff that I've been dealing with for mostly all my PhD, this cross-correlation function. That's the one that is in the paper producing the discovery. Now, how do you get a spectra? Well, you need to build a spectrograph. So let me drive you a little bit what is a spectrograph, then to give you a sense how difficult it is to just do these measurements. Well, first you need a telescope in our case, and you saw it much better with Michel before. We use this telescope, which is almost a 2-meter class telescope. And a spectrograph is an optical equipment, so practically it's a box somewhere with some optical equipments. I made it simple, but I think it gives you a little bit the picture what it is. It's practically the same kind of optical trick you have in your cell phones right now to make a picture, plus something I don't think you have in your cell phones. It's kind of triangle here, which is a prism. That is the machinery that produces the spectroscopy that's going to split the light. Now, all this together, you bring light, and to do that, we have been using a trick, which is an optical fiber. Actually, they're really yellow. That's the color of these fibers from the outside. I don't think they're shielding. And then the light goes in, and what you do really practically, you make a picture of what the telescope is seeing, and this picture, you split it in different color. This is the purpose of this prism, and you clearly see that you have that item. The light is kind of yellowish, which is a mixture of all the line, and then after you get the blue going in one direction and the red going in one direction, you make a picture here, and you produce what is called a spectra. Now, the trick here and the difficulty is anything you change into this equipment, imagine you move a little bit up and down any of these optics, will have an effect on that image. Since your image is the spectra, and that's this image you use to compute the speed, it will practically make a speed effect. So anything you do will produce a kind of a structure, and if you don't deal with that, well, you don't detect the planet. So it's really getting this very stable and understood that make possible the use of the spectra to do the accuracy, to get the accurate radial velocity measurements. To make your situation worse, since this is making an image, well, what practically you do here is you're making an image of that star. The star is like here. So you have to make sure there is no tiny motions of that star. That's the purpose of the fiber, to mix. That's the trick we have been using to get this kind of stability. Now, the additional difficulty is this optic device is used to spread the light. And depending how you do it, you are sensitive to the air index. And we're using a principle which is diffraction element here. So it means the air index is part of the building up of the spectroscopy. So any tiny change of the spectrograph will produce an effect which is way larger than what you try to measure. So that's really why I think the success of discovery is into the machinery that actually built and was able to get this. Now, practically, what we do here, we don't have a spectra like that, and we benefit from this new development in the 90s that's called this CCDs. You have all this right now, or kind of. It's not really CCDs, but kind of, and in your cell phones. And that's the spectra, how it looks like for an astronomer. So we call that Echelle spectra. There is an optical trick to do that, though it's all the art of the opticians to make sure this is what is being produced. The blue is in the bottom, the red is in the top. You see the line? They are there. They are kind of, they appear like black stretch. And the difficulty here, if I make a zoom on one of these line, you will realize that you see the pixel size, if you really the detector structure. And what you start to understand is practically we're working at the limit of the detector, of the resolution of the detector. And if I give you the scale of this, it's 2 pixels here, which is the minimum sampling you need. It's called the Shannon theory to see what you to understand what you're doing. It is 10 kilometers per second. So the effect we're trying to measure of a planet orbiting a star is 1,000 times smaller than that. So practically, we are building an instrument which is blind. We can only make use of it if we use all the piece of information we have together, all the line together, to what's called super sampling and to deal with that. So it's also the global aspect of these global treatments that we're doing, assuming that the instrument is working right and perfectly. That is part of the success here. So here's this beautiful machine, which is now in a box at the Observatoire of Haute-Provence, LOD. You can see it if you go in Haute-Provence. I do recommend the trips. Beautiful place to visit and to spend some time. Good food. And why did we succeed where others failed before? Well, it's a difficult question, but there's a couple of elements here in this instrument, which is absolutely, I think, was the big step forward. And actually, all the new generation of instruments that Michel mentioned, they all build on the same principle. So this is really the beginning of the story, and all the principles here still apply, of course improved, but still apply. Well, the first thing you need to do is to need to have a way to produce this wavelength, and that's the trick, this piece of optic, which is usually very, very expensive. And in the case of LOD, it's called an Echelle grating, and that was the first of that kind. There is plenty of these right now, and that was first of that kind. So if you use that one, and you have a clever optical designer, in this case, André Baran, for us, you can make something extremely compact in the design of the optic, which is a key, because then it's easier to control the stability of an instrument which is only a couple of meters wide than something which is 10 meters wide. So that's part of the first piece of the success. You get what we want. You get the wavelength. You get the stability you want. Now, you use the fiber. You see the fiber, the yellow here, entering into the system. They come from the telescope above. And then there is something else which is not visible here. That was, I think, absolute breakthrough and made discovery possible. Is at that time, you may remember, it's the 90s, came up on the market that microcomputers. That was a true revolution for astronomy, because they were using the chip they were using was called the name Spark. And if you know the Spark system, that was the one being used by the Cray technology, the big mainframe, the supercomputers. So they were available. So very expensive. So we had a very efficient computer, the 32-bit computer at that time, and that allowed us to build an optimized code. And we had to even trick it. We have to speed up the clock of the computer because it was not quick enough to get the data processing of all these data treatments that I kind of suggested to you within 20 minutes. So in a way, we had all the tools together to go to the telescopes, to point the star, and to process the data. So it was really a lot of fun to spend all these nights with Michel together trying to observe the stars and to think about the result. We were doing science live, really, during all that time, and a live measurements of the radial velocity of the object. So practically, the piece of luck, in a way, or the fact we worked right from the day one, we had a machine that was right to the point. They had the 10 meters per second accuracy that was needed for detecting a planet. Of course, at that time, nobody was expecting a short period planet. I'll come back on that, but I think the machine has this capability, and the program started with this. We were clever enough to even produce a trick to track the instability into the object, and that's the trademark, that's the signature of LOD. This is what you get. All the line is the stellar spectra, and you see all these dots, and these dots were a trick we used because we use this to record the variability we had into the spectrograph. It's called the thorium lamp, and this created a concept which is known, very famously known, as simultaneous thorium references. And this branding now is used for mostly all over the spectrograph in the world, trying to do that. Okay, so with this, the program started. We pick up an object, and then we publish this amazing discovery. Okay, so there is a couple of points here I would like to just mention specifically to you. Well, the first one is we produce the Jupiter mass object, But the big challenge of this one is the distance of this object. It was only 8 million kilometers. The orbit of the planet was only 8 million kilometers from the star, which is 20 times closer than the orbit of the Earth, which is still a factor 5 closer to the orbit of Jupiter. So we had a Jupiter, but not at the right place, right? Now, we came up with a kind of discussion in the paper. We say, oh, okay, we have a Jupiter, but in a way it's not at the right place. And it must have moved. We mentioned the term migrated. Or we have to get something bigger and get stripped out. We had no theory for that, but it was the only way we could explain. And actually, we were really in deep trouble. And I want to show you why we were really in deep trouble. And I will try something difficult, which is, I think, to get in one slide the whole planetary theory. So this is what we call the protoplanetary disk. This is where you form planets. Now, what you have to understand here, this is measuring the millimeter wavelength. This is a thermal map of an early stars. And when you see here, it's a bit of a trick because it's only a small fraction of the disk. You see only the particle of the disk here, which is producing heat. It's very, very low temperature. It's 10 to 20 degrees Kelvin, so very low, but still very visible with the ALMA network. And this is where planet being formed. Now, what you don't see here is the bigger stuff, which is the gas, which is invisible on this picture here, which is much more than that. And when you add the gas, what is going to happen is you have a structure into the gas. This is to give you a little bit of the chemistry, where depending of the temperature, you get different flavors. Most of the gases can be in molecular form as well. And there is a very strict dividing line into the disk where the gas becomes so cold that it becomes solid. You have a change of phase. Well, this is an essential piece. If you remember only one stuff about this, you understood everything. Why it does matter? Because the physics of the gas is not the same in that kind of gravitational disk than the physics of the particle. The gas is completely hydrodynamic dominated, and when you press it, the heat goes up, while the particle, they just suffer the gravity. So to understand that, you have to look at the disk on the side, and this is one of the famous disks with beta pictoris. This is the particle. Again, the same kind of particle. It's not the gas, and you see how thin it is. So the gas never got that thin. The gas is much more thicker. So moving from gas to particle is a trick to collapse on the disk, on the mid-plane disk. Because all these particles are collapsing, they eat each other and they glue each other. So the key stage is when you move to the gas, to the disk, that creates the accretion mechanism to build up the core where the planet is being assembled. It's called the core accretion theory, right? So what you could do here is, because of the nature of this called snowline, depends of the nature of the gas, depending if you look at CH4, CO, and 2, you don't build the same particle. So you have, in a way, the snow of water, closer, you see an H2O, or you get the CO2, snow, and then you have the CH4, snow, and so on, and so on, and so on. And what we do have is Jupiter. So we have these beautiful Juno missions, and you can just prompt what is in the atmosphere of Jupiter. And you relate all these components, oxygen, carbon, all this, to this element, and you know by this where Jupiter has been formed. You just look at what is the compositions. And we know that Jupiter has been formed far away, and there is even an idea right now, it's even further away that it is today. So this is really the challenge. So all the ingredients we have are pointing for telling everybody Jupiter has to be formed far away because of this. So you are going against the whole theory when you announce this planet. Now, the other trouble you have is with the nature of the discovery, because you don't get the radial velocity. You observe the global velocity field of the stars. Well, you know there are spots on the stars, and we have this trick to build up these cross-correlation functions. So let me show you if when you have a spot that appears, what is going to happen to this calculation function? You see the function is going kind of change its shape because you have just a spot on it, just to illustrate. Well, this is a massive effect, but if you have a tiny effect, this is what will bother you. So you measure this as a change of speed. And then you believe you have something while you just measure the surface of the stars. And this is the sun. And to give you an idea that the sun is not perfect as well, this is the sun when you measure the magnetic field, and you see, sorry, this is the acoustic periodogram. So you just measure the speed of the sun, and you see there's a structure. It's not flat. There is even a kind of a strange anomaly here that, by the way, match exactly the anomaly when you get the magnetic field of the sun. So we know that a star is not something perfectly flat, so we know there is structure. So the problem we had to deal with, and we mostly spending most of the time of the paper discussing this, so to trying to discard this, saying it cannot be that, it cannot be that. But then we had to face two problems at the same time. The data are really difficult because of that problem to find out that you get a real radial velocity effect, and the theory doesn't back you up here. So if you look back about the history of the discoveries, well, what you realize is the time scale is very interesting. So this is a time scale of all the discovery that has happened in the last 25 years. And you realize that for about the first 5 years, since 95, there were not very much planets being announced. And the reason why, because I think for a long time, people were pretty skeptical about these planets. On one hand, the theory doesn't back you up. On the other hand, well, there is all this weird effect on the surface of the star. So maybe, I mean, this is what you believe you have, but you don't really have it. So it took a long time, actually, to be convinced. And Michel mentioned the first transit before, and that was a real trigger here in 95 when people start to say, oh, yes, no, that's clear. They exist. And you, at that time, started to grow the interest for the topic. The key next time milestone here is when people realize that because we had so much of this small period planet, they will be very likely having a transit, because the closer you are from the star, the more likely you are to be aligned and to detect a transit. It's just the closer you go to something you want to hit, the more chance you have to hit it. That's exactly the idea here. So, and on the ground base, and you see the ground base started to develop with a couple of equipment, mostly in UK and in US. And then the first space mission here, very slim, that was Kourou. Space mission was a breakthrough because Kourou allowed us to pick up the first rocky planet, a small planet. And that was the beginning of the kind of explosions of the planet discovery that you have later here. And you guess what is behind this explosion is this fantastic Kepler mission, which now it's stopped. So that was a completely change, and that completely changed the field. So in a way, the field took a long, long time, to establish by itself, because all these kind of weirdos, all these kind of strange planet that we had found. Now, to try to get a picture where we stand now, and what we have learned, and what does it mean of the discovery? There is one diagram I like very much because it captures a bit everything together, is if I collect all the known planets that has been detected, either detected by the similar technique that I was mentioning, or by the fact the planet is just going in front of the stars and producing a transit, and you get that diagram. So it's two diagrams. Some of the planets have both, and the color is the same. If you remember the color matching, you will get it. Some, they only have radial velocity detection. So you have the period of the planet here, and you have the mass in Earth mass, and here you have the radius. So radius comes from the transit, mass comes from the radial velocity detections. So what is pretty much striking here, if I just overlay Jupiter here, and you realize the transit is failing to detect all the long period planets, which is expected because the transit is very rare. So the other aspect that I think you may have noticed is we failed on detecting Earth. There is a kind-ish one here, but really it is not, we don't have very much. It's not because they don't exist, because we have not been able to do it. It's very difficult to go there, and you get the feeling here of the threshold. So a lot of systematic is this diagram, and you understand that here you are comparing the data which are from space with one from the ground, which is the light blue. The ground was mostly collecting the wool stars you could see in the sky, while here in this case, the space was very deep and having a very small fraction about that size of the sky. So there's not the right same statistics, so it's difficult to read through that. But we can try to do the statistics of the occurrence of each of these planets. So the question is, if I observe a star right now, what kind of planet should I expect to pick? Well, you would have about 1 to 4% chance to pick a planet that would fit in the size of Jupiter at short period, or the mass of Jupiter at short period, which is exactly the one we found 25 years ago. So we picked the tip of the iceberg, and by the way, during my PhD defense, I said, I suspect here we may be seeing the tip of the iceberg, so in a way, that was exactly the tip. Well, now, this big chunk of object here, actually it's a massive amount of planet, and that was the really big surprise, because we know about 50 to 80% of the star that we observe have a planet like that. 50 to 80%. It's really a lot. I mean, it means these planets are different from the solar systems, and they're very common. And then if you look at the radial velocity techniques that can easily pick this long period object and massive, you end up with something about 10%. So we have 10% of objects which are giant planets. Most of them have kind of a weird orbit. They're not really circular like the Jupiter in the solar system. So there's only a small fraction of this one that may be similar to our own Jupiter. So practically, if you imagine you would be looking for the solar system from another star, you would we would barely be able to detect Jupiter only here. All the other planets would be invisible with the current technology we have been using. So that's really the situation here where we stand right now. And that was a big shock, because all this population of planets was not at all expected. And here we're talking about something we don't have counterpart, talking of object which is from Earth to super-Earth, mini-Neptunes, Neptunes, super-Neptunes, mini-Saturn, Saturn. I don't know that on the terminology, it just doesn't make any sense, but it's just to give you an idea of all this spread and diversity we're having. So if you want to understand a bit better this object, we can do something great. We can combine these measurements with that one, because some planets have both. So you make something which is very exciting to do astrophysics. You build up a density, kind of bulk density. So this is the density picture. So we have the Jupiter object here. This is the radius and the mass in this case. And then you go down to the smallest object possible. So to help you, I put also the solar system planet to give you a little bit of visual. And to help you a bit further, I will just draw, if you imagine a planet which is only water, the density, the bulk density of the water, that would be exactly here, which is the water density, 1 gram per cubic centimeters here. So anything which is below this curve, like Jupiter, is more heavy. So I give always example to the classroom. I say if you dump Jupiter in your bath, and they will laugh, at the time they laugh, and this will sink. Well, Saturn is on the other side, actually. He will just float. So this is where you sit, and then the further down you are, the more dense you become. And then you can play the other game. You can start from the Earth and go up and say, what if you take the Earth, keep the density, but you move up the mass? What is the change of the radius? So you understand that you can have Earth, which may be a mass of 10 times the Earth, but according to the density, you would need to have a radius of about 2 times the Earth radius, roughly speaking. So you use that to tell you what is the nature of the planet. And you already understood that if you sit in this area, which is about 5 Earth mass, with 5 Earth mass-ish here, you can end up with object that is denser than the Earth, but also object that looks a bit like Neptune's, but also object that looks a bit like Jupiter, and up and up and up. So that was a shock for the community when they start to realize that you can have a very small object. Having a small object doesn't implicitly mean it has to be similar to the Earth. There is a diversity of the planet way beyond any sci-fi movie they could imagine, which is a good news when science beat the sci-fi, especially in astronomy. So this is a problem we're facing right now. And to give you that from another perspective, yes. this is when you try to cut a planet, what you would expect. So a planet, because of the core accretion mechanism, is a bit like a Lego game. It's assembling pieces together and slowly, piece by piece. And because of the gravity, anything heavier tend to sink when you form the planet. So you end up with a very dense core, which in this case is the core of Jupiter, the core of the Earth, which is the denser possible object you have, atom you have. In the case of the Earth, is mostly iron you get in. Then you get a big chunk, which is called the mantle. In the case of the Earth, you have a similar kind of structure in the case of Neptune's, and also similarly, which in this case is mostly the gas, but the gas has a property that looks like a solid here, a metallic solid here. And then you have the rest, which is what we call the atmosphere. So the atmosphere of the Earth, which is a bit too big, actually there's a bit more thing actually here. You have the atmosphere of Neptune's, which is anything you collect on the top, and then you have the atmosphere of Jupiter. So that was the understanding of the planet we had, and we kind of always think that way, which it has to be an Earth, and it has to be and then a Neptune. Well, the surprise, according to the diagram, I mean, I had to add 2 more planets here. That are not in the solar systems, and I will add 2 more planets. The way we understand it is, for the same mass, I can well have a planet that has no atmosphere, and we have no evidence of some of them that have no atmosphere. To match then the mass, to make it right, you have to increase the core, and then that's a trick I've been doing, and then making the mantle smaller. Actually, I can play all this number all around. It's kind of not well defined. So we're not very sure what we're talking about here, because even the mass and the size is not enough to get the story right. And here, similarly, in the other direction, I can just make it fluffy. And then I get a completely different structure. So depending on the gravity, the density, I can just understand where I fit into this diversity here. So the trick to solve that problem is to get the atmosphere, because you get it that the atmosphere is different from that one, and that one. And here we use a transit. The transit is a fantastic tool, because by the time you are on the transit, you can use the fact that some of the light is being absorbed by the atmosphere of the planet, and you can detect that. You can also just wait the other direction, just the planet goes behind, which is called the day side of the planet, and at that time the planet is reflecting a lot of light or is emitting a lot of thermal flux, and you can use that to understand the atmosphere of the planet. So all this idea of the atmosphere is essential for another concept I would like to introduce, because it's all over into the media these days, is the concept of habitable zone. So the idea is that in the 60s, people started to think about the possibility of losing the atmosphere, or having the Earth, you could remove life on Earth by moving the orbit, by getting closer or farther away. If you go too close, practically you evaporate so much, so you lose all the water in the atmosphere. If you go too far away, you get too cool, and you end up with a kind of ice ball, and everything froze, and there is no life. So that defined, in the case of the Earth, a boundary, which is called the inner and outer boundary of the habitable zone. So everybody had this in mind, and if you look at the habitable zone, I think for the Sun, you will be around that region here, but the problem is all the planets we have detected doesn't fit into the habitable zone, because they are very close. How about I show you before? So we have this embarrassing moment right now when we're talking about habitable zone and want to use it as a concept. Well, you don't have very much planet to deal with. So the trick we've been playing is that the habitable zone depends of the amount of energy from the sun that is beaming on the planet. So if you take a star which is a bit smaller and cooler, you will have to be closer to get the same amount of energy, assuming all the assumptions made for the habitable zone are valid, which can be debated quite a lot, I must say. So in this case, when you move down, you're entering into a possibility to get some planet that may fit for the search for life. And this is what is going on these days. We're detecting planets, and you see some of them here, that fitting in this habitable zone using that concept. So I think we're living a kind of a moment right now where we're just starting a fantastic stories, and we're having a kind of a big questions right now we're trying to deal with, and we have opened the window with. Is first, these questions about how do planets form and evolve? I think you got the picture here that we far to understand everything. We just pointed that there are some disagreement with the understanding of the formation in our solar systems, which is fine, but the key question is more the opposite, is, well, why the solar system is what it is? so different apparently from all the planets we have found. We don't know yet how different. Maybe it's kind of a few percent, maybe it's very rare, maybe it's 10%. It's still open for debate, and we're going to fix it in the next 20 years, I'm pretty sure. We will know, we'll find this system. Now, but this is really interesting for the question of life, because we may not have this conversation today if we would have ended up the same way than the other systems, which is more common. Well, the second aspect is there is an intrinsic diversity, and I mean, how do we fit in? Really, what is the meaning of this? So we understood already a lot, and that's part of this big debate about the extension of the Copernican revolutions, and we keep going along this way. I think it's very, very interesting, this debate, and it will keep on, and then it drives to the next item, which is the relevance of life. And here I would say there is really a couple of elements here to put together. First, there is the origin of life on Earth, which is fascinating, and I think by exploring the solar system, we may have big surprise. So I really encourage you to only focus on exoplanets, but also to focus on the solar system planet, because they are amazing. I mean, Venus, Mars. I mean, some satellites of the giant planets. Now, it's not only about the origin; it's also about the prevalence. I think. I mean, if you look at Venus, there is a serious idea that Venus, 1 billion years old ago, was very like much the Earth. So this concept of life may come and stop. It's very interesting to study, and again, by looking at so many possibilities, so many planets, is a way to explore this possibility. And then there is even more difficult question, which is the nature of life into the universe. So we very practical, for practical purpose, very kind of focused right now on the life as we know it. But it doesn't mean that this is the life in a kind of generic term. I mean, for me, life is just kind of a chemistry experiment that turned bad because it took control of itself. So we play with some chemistry here. We end up with amino acid on this. There may be other kind of chemistry going on. I'm even still with the carbon. I'm not trying to challenge here funny chemistry. So I think we need a lot of help here by the chemists, by the earth scientists, and that's a revolution going on. I think it's more than the new field of astrophysics. I think we're entering a new field of science, which is studying life on a more global way than only in life as we know on Earth. And I would like to conclude this talk by saying how fortunate really I am to have such a great family here today with me, and wonderful wife, and without their infinite support and patience, you know, it's not always easy to be living with a physicist, and love, I guess, I would not be standing here today. So I really thank you for your attentions, and I wish you a joyful, entertaining Nobel Week. Thank you very much.